will like in a few minutes.
All right. Should we wait?
No, just go on.
Okay. So how it is imagined is, so this is a consultation hour. So we are here for you, both Professor Gurikov and me, and if you have any questions regarding some general organizational questions regarding the exam, or anything that remained unclear from the exercises or lectures, then we are here to answer your questions. I have received some emails also from some of you with a couple of questions. So maybe if you are here, it will be good to ask, and then we can maybe discuss together. Who wants to start with questions?
I had a question regarding the cone equation. In that, I've seen in the book sometimes they use the salt concentration directly instead of using the ionic strength. So I was a little confused about that. That when should we use the ionic strength, and when should we use the salt concentration directly?
We will, in this case, so if you get such question, it will be given the exact equation you should use. And yeah, we have been working with ionic strength simply because, yeah, it's taking into account the property or the dissociation of the ions. Yeah, depends how it's expressed, but most probably in our cases, we're going to use ionic strength, and it will be given in any case.
And basically, this change only changes the constant, yeah. So because the concentration and ionic strengths are always directly proportional.
Okay, thank you.
Ma'am, can you hear me?
Yes, we can hear.
I have few questions, and I have also sent an email. Maybe I will ask now.
Yeah, I remember. Do you want us to go question by question, or do you just want to proceed and?
No, as it is easy for you, no problem. I have sent you an email. Maybe we can go through it. I was going one by one, yeah.
All right. Just a second. Yeah, I have your email. So the question 1 was regarding our solvent extraction exercise.
Yes, ma'am.
And you have a question regarding the slide number 12. How lower feed to solvent ratio will affect the operating line? Now, I will just maybe, if you guys give me a second, try to share so everybody remembers what we are talking about. But what I warmly suggest with this task is for you guys to maybe try and play a bit with the values that you have in Excel. So you can maybe plot, you have all the data to plot the equilibrium line and operating line, and then maybe by yourself you can change and recalculate the yield. You also have, we didn't calculate the yield directly in the task, but you have all the information. You have the concentration in the substrate, you have the concentration in the feed. So you can very easily calculate the yield and compare what happens when you change. You can change F or S, make one bigger or make the other one smaller, and see how it will result on your concentration in the substrate phase at the exit of the extractor, and you will see that you will indeed get a larger yield. You can also see that even if you apply only the equation and just plot maybe a few points and a few values, you will see that the end point is going to be higher than for the feed to solvent ratio that was given. But the question in this case is just a second to find the appropriate. Sorry, I have to do it from the. All right, now I can share with you guys. You see the solvent extraction slide, I believe.
Yes, ma'am.
So what you should do is you have the equation. Let me just for a second share the exercise as well itself. So you have the equilibrium relationship given. If you plot x, you can just put some arbitrary values for x from, let's say, 0.0 to 1. So maybe you choose 5 or 10 points. So you can plot the equilibrium line, and you can also, with the equation that we calculated in the exercise here, you can also find the values or the concentrations of the antibiotic in the solvent at the exit. And if you plot, the operating lines based on so you have equilibrium line, you take arbitrary values. Here we also have the values. And you also plot for the operating line, you actually would need only 2 points. And you guys can play with the values and recalculate the yield for each case. So try to alter this F to S ratio here in the operating line equation. So you can, I think in this case, the feed flow was 550 kilograms per hour and the solvent flow was 110. So you can make either one smaller or bigger, or and see how the line would change. And you see that you will get something similar that we have here, and that indeed your yield in the end would be higher when you as well calculate it. I hope I managed to clarify this a little bit.
Ma'am, actually I wanted to ask this thing. For example, there were two questions. One for the mixing, that if we mix, so it makes sense in our mind that I can play with it. Like if we do the better mixing, okay, in the extraction there will be higher yield. But I could not play with F and S. How should we, like, mentally, how should we make the picture? How it will decrease like this? Like for the better mixing, I did not do any calculation. I know that with the better mixing, maybe extraction will be more like this way. Is it possible, or should we have to draw if there is any?
You simply need 2 points to you don't need to draw. This was my just suggestion for the visualization of the task. It would be nice for you study to actually try this for yourself. But you do not need to draw. You can simply calculate. Just change this value, and you would see that actually your concentration in the outlet would indeed grow. And for you, this is also to see as an information to have it in your mind, that indeed with a lower F to S ratio, you would have higher yield. Is now kind of better?
Yeah, yes.
All right.
I will try it on my own then.
Mm-hmm. You're welcome. Okay, anybody else has a question to solvent extraction while we're here?
Yes, just one question about it. If you go out into the slides, Yes, in the first one.
Mm-hmm.
Yeah, exactly.
Mm-hmm.
Fifth page number.
Fifth slide. Mm-hmm.
Yes, I would like to ask you here. Now, the mass flow rate of the solvent is equal to the mass flow rate of the extract, and also the mass flow rate of the feed is equal to retentate, because I think we assume that the solvent and carrier are completely immiscible, right?
Mm-hmm. Yes.
Yeah, that's I just want to mention something.
Yes, but be careful here. So in this case, in our exercise, it is stated clearly in the task. First, you have that your feed material is not miscible with your solvent, and also you can see that it is quite a diluted system. Let me just find the concentration. Yeah, so you have only a few grams of the component per kilogram of the carrier. So it's in general the mass transfer of this antibiotic would not significantly. So even if you take it into account, you would get that you would have point something change in the flow. So in this case, we can say that we can neglect the influence or the changes in these flows, or so we can say that the feed equals to raffinate and solvent equals to extract. In case you have a more concentrated system, and of course, if we also give a phase diagram, like you can see in it's not a test exam, is the exam I gave you also, I uploaded also on StudIP for you to practice. You will see that also phase diagram is given. You can clearly read all the compositions of the phases, and in this case you need to calculate actually, or to take into account all the flows and how they change, because we cannot neglect the mass transfer in that case.
Okay, perfect. Thank you.
You're welcome.
That's actually a very general. Thank you, Annie, for pointing this out. So in our lectures, we did not consider that these capital letters can be influenced because of the mass transfer of the solute, into another phase, So we always close the balance based on the compound to be extracted, and we also close the mass balance based on the flow rates and the solvents going into the unit. But in fact, in very general case, we have also to take into account that we extract something, and physical and absolute mass of the certain flow changes, because even if they are fully immiscible, that's an issue. But you basically have to keep in mind this is also possible. Thank you.
If further questions, maybe regarding the same topic, or we can proceed with the questions I received from
I have one question. How do we define the yield for this specific task?
Well, you always define yield by, you divide what you have extracted towards what you have at the beginning, right? So in this case, what is at the exit of your system is this extract phase. So the mass of antibiotic in this phase over what you have, the concentration or the amount that you have in the feed. All right. And you have given more or less, I think, all the values. So yeah, this we calculate in the end, and this you have given, and you can, from these two or these 4 values, calculate the yield.
All right.
Further questions?
Hello. I have a question.
Mm-hmm.
So, on the exam question task 2 on the 2021 version, it's tasked to liquid extraction. On the solution, you have the answers, but I think I'm still trying to figure out how you came up with those values for the composition for M1, based on just like, what you have as given. Just really couldn't connect, how you got from what you have given in the point. Yes.
Let me just share for a second. But basically, the whole task is based on first knowing how to read the diagram, and then as well setting up the mass balances. Let me just find. What is actually confusing me more? How to read the diagram itself? Or?
Yeah, I mean, I know that's not going to be, given, exact values, and then I know we have to come up with some relationship here, but I think I'm just missing like which equations or which mass balances to look at, because I think I'm okay with reading the ternary system. It's just the actual point, like that 3D compositions. I don't know how
let me then just quickly open the exam. All right, this is the task we are talking about.
Yes, correct.
All right, and you are wondering how we came to the composition of M1.
Correct.
All right. So basically, to read the diagram, you need to follow the lines given already on the diagram. So to read, let's say we are at the point M1. Here we have butyl acetate. Here we have a broth. And here we have our antibiotic. Now, if we are here, broth is read for the composition on these, on this line here. But it's actually the hardest one to see because it's a bit cut out. But instead, of course, all the fractions need to sum to 1, so we can calculate it later. What we can see, or what we can read, is, so if we go to the right, you can actually read the composition or the mass fraction of the antibiotic. So here we read approximately we said 0.28. When you go down this line, we read butyl acetate, which is, the concentration is 0.3. And then here, if we could see the whole diagram, you would see, and we do see that it's kind of 0.6, 0.5, it's going to be 0.40 something. And since these 3 need to sum up to 1, then we can also calculate, instead of reading the diagram, that the concentration of the broth, or the mass fraction in this feed of the broth, is 0.42. All right. And the same you do for the raffinate and for extract. And you use the same lines to read the concentrations.
I also had a question here. Aren't the raffinate and extract marked reverse in the diagram compared to the composition?
I'm sorry, everybody, this is right. I will correct it and upload a new one. Yes, so keep in mind, raffinate is here, extract is here. I reversed the letters. Yes, thank you, you're right. All right. Is this more clear?
Yes. Okay.
Okay. You're welcome. right, further questions? Or should we go back to the previous question list? So, okay, this is also related to the extraction, so I will just proceed with it. Tayab had a question regarding the ATPS, and actually questions 3.1 and 3.2. If I remember correctly, this is then the cloud point extraction.
Yes, ma'am, it is.
All right. Just a second, so I find. All right. All right, so this is it, right?
Yes, ma'am.
So what we had, let's just go a little bit back. What we had in our system, so the first part of the task is related to the actual extraction of our peptide in an ATPS, and this part of the task, so 3.1 and 3.2, are related to the recovery of our EOPO polymer that we use to extract our peptide from the initial solution. So now we did an ATPS, so we had our extraction. Now we only take the top phase, which has our peptide and EOPO, and by heat we can actually recover this EOPO polymer and separate it from the protein and the remaining water, because now here, of course, we don't have pure EOPO, as we know from such phase diagram. So we know that, so EOPO is in the phase 1, in the top phase, and this is EOPO rich phase. But in this phase, we also have some, of course, we have our extract, we have some water, and we have some starch. And from here, we can read that the concentration of EOPO in the top phase is, we read that it's 12.7 weight percent. Okay? So we know the concentration of the top phase, and this is this fraction here. So we then take only the top phase, and now we want to just extract or at least get an EOPO rich phase. And we can do this by cloud point extraction and by adding heat, in this case, heat to our system. And this is what this part of the task is about. So we are done with extracting our target molecule. Now we want to recover our polymer phase that we use for the extraction. And we can do so, and we know how the system behaves from such a diagram. This is a diagram with, this is called lower critical solution temperature, and it is telling us at which temperature we are going to have a phase separation. So in this area, we have only one phase, so we have our everything mixed. Let's say we have EOPO and water to simplify. And when we heat, we are going to have two phases. This phase on the left, or all these points, is a water-rich phase. And here on the right, we will have an EOPO-rich phase. Okay, is so far clear?
Yes, ma'am.
Okay, good. So the first question is we need to determine the cloud point temperature from this figure. And as I reminded you, we know that the composition of this phase, or the mass fraction of the EOPO, is 12.7. And this we know from this diagram, or where we can better read it from is here. So here we see that we have 12.7 EOPO in this phase. Okay?
Yes, exactly, ma'am. Now I know.
Okay. And this is how, so we just take here is 10, this is probably 12.5 and a little bit on the right. We approximate, this is 12.7, and then we determine that the temperature here is around 50.25 degrees or so. Okay? So this is the first part of the question. And in the second part of the question, we need to use this diagram to determine at which temperature we need to recover, to recover more than 80% of EOPO. Now, recovery, or so we need to get our EOPO, as I said, from this EOPO water product mixture. And yeah, we are using the two-phase diagram for that. Now, this is now only done in exercise so that you guys practice calculation of this type of things. But of course, in the exam, we're probably not going to give you to iteratively in such way get to the solution. But so since we don't know the temperature here, we have to try several different temperatures. And the recovery we define as mass of our EOPO in the extracted phase, so in the EOPO rich phase, over the mass of EOPO in the initial, this water EOPO peptide solution. Okay? And here we gave 52 degrees as an example. So you can also try and do it for other temperatures and find this recovery temperature, because here in the exercise we just demonstrated, but we actually haven't given you the temperature. It's going to be probably a bit higher than 52. So what we have, how we can calculate the mass in the extract phase is mass of this phase times the fraction of the EOPO in the polymer rich phase over the mass of the initial solution times the mass fraction of EOPO in the initial solution. We know this, it's again 12.7, this is what we already said. This value we read from the diagram, so we know, as I told you, on the right side is the polymer rich phase, and we read that it's around 32% here. We are looking at 52 degrees at the green line. And this mass of the polymer rich phase versus the initial mass, we can apply the lever rule that we also learned on the previous slides. And it tells us, and this lever rule can be actually applied to any diagram. So it's we demonstrated it on the ATPS diagram, but it can also be used here. And it tells us that the mass of this fraction, or the length of this fraction over the length of the whole line is equal to the mass of the polymer rich phase over the mass of the initial phase. And this is how we get this MPP over M0. And these units you can use, if you have a ruler, you can use centimeters, or here we use these cubes, it doesn't matter. What we care about is the ratio. So here we said it's 1 to 3 units over this whole length is 10.5. So we have 10 up to here, and here 0.5. And this is all. And we got that the recovery is 0.72 or 72% at this temperature. So we need to try further other temperatures to get 80%. Was this better now? Is it clear?
Yes, ma'am, it is clear. Just a little bit question, one more. That we have done this when we already know the temperature, right? 52 we already know, then we have calculated all the other concentration and the masses.
You arbitrarily choose the temperature because you need to find the temperature at which you can extract this much. And we see, actually, we have less here, so this is not our temperature, right? So we chose. You should try the red line, the purple line, or choose whatever is up to you. It's arbitrary.
So this type of question will not come in.
We can tell you, we can ask differently. So, for example, what is the recovery of EOPO at the temperature of 52 degrees? But then you need to know how to do this. What I said that we will not give you to do this in this iterative manner, because you need to calculate the same things many times to get to the right temperature, as you saw. Because here the chosen temperature wasn't appropriate, because it allows us to recover on the 72%, so it doesn't fulfill the stat that we have. But if we give something like this, we would just formulate it differently, so you don't have to do the same calculation over and over again and search for the point. I think it's a bit of waste of time. We want to test how well you understand and know, and not just make you write a lot.
Yes, ma'am. Now it is clear. Thank you.
You're welcome. All right. More questions to this? Okay. Good. I had a question, then maybe we can go back to Tab's questions regarding the precipitation. And the question is, why did we choose? I believe what you mean here is why we chose the salting in salt. Just a second. I believe I just have to double check. Tab, if you are here, please confirm.
Yes, ma'am. I'm also opening.
So the question was why we chose this salt, correct?
Yes, ma'am. Actually, yes. Why we have choose the NH4I, ammonium iodide?
Yes. So, and you say because we had a negative value. So this is true because the value of the solubility constant is negative. Why? Because in the end, when you rearrange the equation and you want to express the solubility of our target enzyme, you get this. And of course, you want this exponent to be as high as possible and positive. So first, in order for it to be positive, you have to minus. Exactly. It needs to be minus minus. And yeah, so you want it to be as high as possible. If we gave you two salts, for example, that have both negative values, then you want, so this solubility constant and this ionic strength to this this part of the equation to be higher, to have the stability of your enzyme.
Yes.
Okay.
Yes, ma'am. So the most negative value should be the answer.
Not in a way, but you need to pay attention what concentration we've given you as well. So as I said, this part needs to be higher. So maybe we give you, I don't know, maybe this is -2 and this is -4, but the concentration here is very small. And then you need to test to calculate this part. And the one that has a smaller or the bigger positive value, so minus, so the more positive this part is, the better it's going to, the more it's gonna solubilize our enzyme. So you need to just double check. It doesn't, depends on the both values, not only the negativity of the solubility constant. But negative solubility constant would mean that it would increase the solubility of our enzyme. Yes. Okay, more questions to this? All right. Also, Tab, you had a question, how to make the operating line. Was this a general question?
No, ma'am. It was not a general. It was related to the adsorption, where we have drawn the adsorption isotherms. And actually, my question was like this. First of all, my question is this: in this adsorption term, that what do you mean when you say that we are going for the linearization? What does it mean that linearization? What does it mean that we are going for the linearization?
This means that you need to make these equations linear. And for this, guys, you need to consult a little bit of math. How do you make different types of equations linear? And you do so by doing the same operation in a way on both sides. And I really suggest you guys to look this up or to revise your previous math knowledge, how to linearize the equations. Because here, when you have an exponential equation, for example, you would want to do a logarithm on both sides. Because based on the rules of logarithmic operations, you would then get such an equation. And then if you plot logarithmic values, you would get simply a line. And this would help you determine all the necessary constants. So this is a very common method for such problems, and also for like it's used in chemistry and for adsorption as well, and in similar cases. So, and also when you have an equation of such kind, then there is also a different procedure for linearizing such an equation. This is what we meant. So the equation is kind of the sense and everything stays the same, but you linearize it so you can plot and obtain a line. Or, yeah, linear trend of the values. I hope I managed to make it a little bit clearer with this, but if you want to know why it looks exactly like this, and but I mean, basically for our course, you don't need any more linearization techniques, and this is the most important anyway, how to linearize the values. So it's maybe look up a little bit in some literature, but basically this is all you need to know for the exam and for this course.
Yes, ma'am, I got it. And my actual question was this: the operation line. Can you please go to the operation line part, the last one? Yes, ma'am. Here. So the green one is the operation line, right?
Yes.
So, ma'am, how did we draw this diagram? Where is the equation for this? And because we have the two loading data, Q values were the two, then why don't we have the two operating lines? Why we have only one operating line?
No, the operating line we always based on, let me find just a second.
On page 2, yeah.
Yes, from the mass balance.
Even in the mass balance, we have the Q, right? So the Q, we have the two Qs. We don't have the one Q. We have the two type of loadings, even in the question. Yes, here. Loading Q1, loading Q2.
Yes, but if you but this Q, it's a different type. So operating line is not giving you the equilibrium values. Operating line is based on the mass balance and on what you have. So when you have an apparatus, what you have on your inlets versus what you have on your outlets in both phases.
Yes,
right? And we, the quantity of added adsorbent is one thing. And so in this case, we assume that we kind of added the same quantity of the solvent, but how this compound is going to adsorb. So this Q quantities depend on the interaction between the compound and the absorbing material itself. And you use different principles for operating and for equilibrium line. So, and I explained a little bit here also how you determine the equilibrium line as an example. So you bring the adsorber with your solution in contact, and you leave them for a very long time until you reach the equilibrium. This is why we call it an equilibrium line. And this is the maximum you can, the amount that you can absorb or extract or remove from your solution. And then you measure simply what you have in the solution and calculate how much you have in the solution and how much you have absorbed, and you get the equilibrium line. But operating line is not it's something completely different, because it will depend on your process parameters and on your apparatus itself. So we calculate the operating line based from this mass balance of the inlet and outlet streams. So this is not the same values. I'm not sure. Yeah, we don't have the full procedure here, but maybe I could add it for next just for the demonstration purposes. It's two different how to say, yeah, two different loadings, and we're speaking about different processes. So equilibrium conditions are one, and operating concentrations and these values are something else. Did I make it at least a bit more clear, or should we try another way?
Ma'am, I'm still confused a bit. I'm sorry, maybe I'm not getting it right. But the thing is that, for example, we are using this operation line Q is equal to Q naught S by A C naught minus C. So still we have the.
Have you tried to calculate this task by yourself?
Yes, ma'am. Yes, but I could not. I have done the other things, but operation line I'm unable to. Like, which data should I use? Which numbers should I use to get the? Or is it like the same like in the solvent extraction that we have just two numbers at the end and at the
exactly. So you can just use two values, and you just So it's for operating lines you can use two values. If you need more about this topic, maybe you can really scan and send me what you have done, and then I can maybe in written try to clarify this better. Okay?
Yeah, sure.
Okay. Good. More to this topic, or should we go next?
I have a doubt regarding the theory part of adsorption. Like, I could not understand pore condensation.
Sorry, I didn't get which part?
Capillary condensation or pore condensation in adsorption.
Okay, but
not from the exercise. This is from the theory part.
All right, maybe
from lecturing. Yeah.
Yes, I think she refers to the lectures.
Mm-hmm. So what is basic idea of this capillary condensation? So what happens when we condense or when we observe that the liquid gets condensed? So we see that compared to gases, all molecules lose 3 degrees of freedom. This basically they still can jump from one place to another, but they still can rotate, but nevertheless they cannot freely move like in the gas. And this basically macroscopically we observe as condensation of a vapor, saturated vapor in this case, into a liquid phase. And what happens if you have very small pores, which we classified as micropores, which are smaller than 2 nanometers? Basically, the size of the pore is comparable to the size of the molecule. So molecular sizes, as discussed in the very first lectures, are approximately like in the range of 1 nanometer or less, and depending on the type of the molecule. It means that only few molecules fit into the micropore. It means that they are very much influenced by the attractive forces from the pore wall, and that is why this attractive forces are the reason why they lose some translational, people say translational degrees of freedom, so they can't really move freely. So they are in the field, the attraction field of the pore wall, and that means that basically they behave like liquids, like quasi-liquids, if you want. And this state, when a few molecules are very strongly attracted to the pore wall, and they're sitting here, maybe few, 3, 4, 5, and when they fill in completely this pore, that's what this pseudo-liquid phase, formation of this pseudo-liquid phase is called capillary condensation. So usually the phase which we observe in this pores, micropores, are compressed when compared to standard, like usual liquids. So they actually, the distance between the molecules is even smaller than in liquids at one pressure, at 1 bar pressure. This is again because of very, very strong influence, very, very strong attractive field of the pore walls, and local density of these liquids hence is high. So that's the only, so to say, qualitatively important observation which you need to get out of our discussion. So and this is the reason why we classify into micropores, mesopores, macropores, almost free mass transport, because the diffusion length is much smaller than the pore size. In an opposite limiting case, we have very, very big influence in micropores, and then somewhere in the middle between 2 and 15 nanometers, we classify those pores as mesopores, scale pores, mesopores, it's called mesopores. Okay?
Okay, thank
Does
you.
it answer?
Oh, yes, thank you.
All right. More questions to this topic?
Anything else? Seems to be on the case.
All right. I have a few more questions from Tayeb, if he's still here.
Yes, ma'am. Yes, ma'am. Yeah.
Okay. You had then the last question of yours was regarding the capillary.
Electrochromic.
Exactly. And I'm not sure if I understand your 5th question, but maybe you can clarify it to me. But I can answer your 6th question, which was related to this value here. How did we get from these units to these units?
Yes, ma'am.
And yes, so what you should use here, the SI unit that is marked with A is ampere, which can be broken down to more fundamental units, and we can write it in kilogram meter square per volt second cube. But we will not expect you to know this in the exam, but we would rather adjust this constant here so you get directly these units. So yeah, just for the record, so you know this is ampere. It can be, so if you know how to break this down to these units, then you can derive this, but it's not easy, and we will not give it in such way.
Yes, ma'am, because I was thinking about the V is equal to I, or potential is equal to current into resistance, but at that time it doesn't make any sense then. But you are right, yeah.
Mm-hmm. Yeah, don't worry about this. And you told me 5th question, how here we have to divide by Avogadro's number, but why are we multiplying? We divide here.
Yes, ma'am. It should be multiplied, because if you look at the unit of the mass, for example, 0.1521, it was kg per mole. So the Avogadro number should be multiplied so that the mole and mole can be cancelled out each other, and then we have just kg left.
We have cancelled here. Mole per mole.
Actually, the mole and mole is divided, but the 6.02 into 10 raised to the power 23 should be multiplied, because if you look at the unit of the M, the capital M, can you please go ahead and look at that?
Oh wait, sorry, I need to take a small look into the actual task. Just a second. I will stop sharing for a second just to try to find my files, or maybe we can actually do it from here instead. All right, maybe this is a better slide.
It is on page 2, ma'am. The unit for the mass. Yes. The molar mass M is equal to gram per mole. So we converted it into the kilogram per mole, right? So no problem. But the mole isn't divided. So if we want to remove the mole, the term mole, then we have to multiply it with the Avogadro's number, so that the mole divided by the mole will be, cancelled out. But you divide it by the mole.
I think we should. I mean, in my on this, I have to have a look because I'm still not completely. Can you maybe send me how you derived this? So this part of the calculation. So so how it is and how you think it should be. So I maybe more better understand what you mean.
Yeah, sure, why not?
Okay, then let's do it in written.
Okay.
But yeah, guys, check the units if you have not already. But in any case, it will be given in a simpler way if it comes in the exam. In a more straightforward way with the units and everything. All right. These were all of your questions. So do you have any more? And also if any of you has any more questions, then feel free to ask.
I have one more question.
Tell me.
From the test exam and solution. And if you go there, there is one solution where you have linearize again the one equation. I could not understand. It is such a big equation, but how can we linearize that one? Yes, yes, ma'am. Yeah, this is question. This is part 3, linear fit of the experimental data, and then then it's a very long equation.
But for this, you guys need to know a little bit of math transformations. So this is not for it's not the linearization, so it's not the same. This is actually kind of comes from an extrapolation equation. How you obtain values on the epsilon axis from the initial values on the epsilon axis plus the values on the x-axis. Again, if this you guys should kind of understand based on the math itself. But if you need me to break it down for you more or something, so have a look please by yourself and maybe consult a bit the internet about the mathematics behind this. But if you cannot, then write to me and I can help do it for you in written, okay?
Yeah, sure.
All right. Good. So this goes for all of these calculating issues. Of course, we expect you to know some fundamental math. But of course, if you're having any troubles, and if you have direct questions regarding the calculations, something that I cannot so quickly maybe see here, write it to me via email. That's always better for such questions. Okay. Does anybody have any general questions? Any additional ones that we haven't discussed?
Hi, can I ask a question? This is regarding lecture 10 and 11. It's the bioprocess development, and then the trends. What would be the biggest takeaway for this lecture, sets of lecture? Because I know we went through the whole process development of insulin, and then we have other examples as well. I'm assuming that we don't really need to know the detailed, setup for all these process flow diagrams, but just kind of wanted to get an idea of how should we look into this lecture.
Yeah, basically it's not going to be part of the exam, and we are not going to ask about details of any production steps. The goal of these lectures was actually is to give you an idea how complex actually, how many factors we have to consider when we design process from pure chemical things, how yield is affected in each step, and how many steps we have, how many flows, how many material flows, energy flows, which we actually less discussed, are required to be taken care of when we discuss or design every process. So it's not going to be part of the exam.
Okay, thank you.
Anything else?
I see a question in the chat. He says, I have a short general question. Is it a problem to answer in German in the exam? I would say no. So of course the exam is made and it will be in English given. But if you have difficulties or if you think you can express yourself better in German, do so. All right. Any more questions?
Perhaps for decimal places we stick to English conversion. Yeah, so we have not comma but full stop, because it can cause some cases misunderstanding. Yeah.
I had one more question. In the concentrations, in some questions we are supposed to find concentration. So does it matter whether we use the lever rule or we use equations?
No, so you just should reach the answer. If it's not explicitly required of you or told in the task, use this method to find an answer, then you are free to use either one. Okay. All right. Then, if last chance, if not, then we would close the consultations for today. Okay. Of course, we are at the disposal for you guys. If you have further questions, you can always write. And then we see you guys on the 16th of March on the exam. Good luck with the preparation, and we are here to help with anything.
Thank you so much.
And have fun.
Yes, all right. Bye, guys.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.